our ability to observe the atmosphere with respect to methane, carbon dioxide, and other atmospheric pollutants is increasing. And we can do this from the ground, we can do this from airborne, we can do this from satellites, we can do it from mountaintops. But really the idea is, how do we put this into a framework, right, where we are assimilating all of these observations in such a way that it's giving us the most benefit. And when I say most benefit in terms of basically decision support. And this, goes from the, national or state regulators who are putting together the inventories to specific facilities, specific operators who are trying to understand their greenhouse gas emissions and, potentially want to mitigate them, or at least recognize what the actual emissions are. And so I'm going to present a framework and some examples of success we've had from that framework in Los Angeles. And I'll do that in the first part of this talk. But then the second part of the talk, I want to get into really the next generation, which I see as being, not just from the ground to the surface, that's the same thing, from the ground to satellites, but from being, coordinating among satellites, trying to piece together as many types of observations as we can. And it's really this data fusion that I think is going to unlock any sort of potential or any hope that we might have in order to monitor and ultimately reduce greenhouse gases. And a lot of this is extensible to CO2, that's why I keep bringing it up, but I'm really gonna focus on methane for this talk, which I think is what this group is really interested in, so that's good. Anyway, so the first part, synthesis in the LA Basin. And, why do we do LA Basin? Is really, it's one of the better observed megacities or just regions in the world in terms of greenhouse gases, and that's because we have observations at multiple scales. And so when I talk about, this picture came out a little low res, I apologize, but when I talk about a multi-tier or multi-tiered observing, I alluded to it, it's basically a combination of this, right? We have satellites, we have surface towers, we have airborne, we have on-road surveys. We basically have all these different types of ways to observe the atmosphere. And I'm sure most of you are familiar with them, but I'm just going to start from the top and go down. Satellites really in the last few years for these, our capability of being able to get a global constraint on methane has just expanded tremendously, thanks primarily to the Tropomi instrument. So we're getting 7-kilometer spatial resolution, daily overpass, obviously assuming clear skies, of methane concentrations. And that's an unprecedented amount of data that we're getting about the global budget from this instrument. But that didn't stop us previously. We have great studies using GOSAT and great studies using Schiamaci. But really we're entering this new era prompted from Tropomi that we can start getting at sub-basin scale methane concentrations. Moving on, we also have towers, right? And so many people spend a lot of time thinking about towers, tall towers. So here in Los Angeles, we have the Los Angeles Megacities Carbon Network, which has a bunch of Picaro instruments sitting on top of these 50-meter towers that are spread all across the basin. And they're observing, most of them at least are observing methane, CO2, N2O, carbon monoxide continuously. 24 hours a day. And we also have a few background sites. And so if you have a few background sites and you're pretty well situated throughout the basin, you can start doing regional inverse flux studies. And I'll get more into the details of how I think of inverse modeling, but this is just, so on the left are the locations in LA where we have those towers. On the right is a study put together by my colleague Vineet Yadav, who I think is I don't know if he's a graduate, but was formerly associated with Stanford, but where he did a basin flux inversion using this tower data for methane. And so these contours map out, emissions of emission rates within the basin. And, I won't go into the details of the study, but basically, what he was able to find, unsurprisingly, was that if you aggregate the basin into a few boxes, these are these red boxes, you can start seeing some dominant trends that you can correlate with the type of facilities that are in there. But even if not even on that granular level, you can start looking at a mega city like Los Angeles, and with a good network of spread out towers, say, okay, what is the burden that just Los Angeles is producing? And that's important. And this is a mixture of sources. We have landfills, we have refineries, we have oil and gas, we have agriculture. There's a lot happening in the Los Angeles air basin. But again, you're limited here for this flux inversion by the number of towers you are and resolution. And that's the same thing you have with Tropomi, right? Tropomi, at best, you're getting these you know, 7 by 5 kilometer pixels, right? Which for a isolated point source might be sufficient for you to disentangle, you know, exactly where it's coming from. Similarly with this flux inversion, he's running this inversion at about a 5 kilometer spatial resolution. So 5 kilometers is good, that really gets you down, but it doesn't get you right to the exact source of what's going on. And that's where, you know, we've had these advances in airborne remote sensing that have really been, you know, I don't want to be biased, but pretty transformational in terms of being able to do source attribution and emission quantification at the same time. And so I'm showing a figure here from my colleague Riley Duran's paper, California's Methane, I can't remember the name of it. Well, it doesn't really matter, but it's a Nature paper about super emitters in California that Kelsey actually, you know, worked extensively on, and she probably has some horror stories she could share with you of trying to do accounting of all of these emission sources. But basically, they took their airborne instrument, AVIRIS-NG, so Airborne Visible Infrared Imaging Spectrometer, which is much different than, well, it's not much different, but it's the same principle as something like tropomi, right, where you're measuring solar backscatter, and where you're sensitive to methane, so the 1.6 micron or the 2.2 micron bands, that's where you have these methane absorptions. If you run a retrieval there, you can get something about methane concentrations. The difference is, something like AVIRIS was not really designed for methane, meaning that its spectral resolution is 5 nanometers, compared to something like tropomi, which is 0.25 nanometers, right? And the reason why tropomi is such a fine resolution is it's really trying to get a good precision on the methane absorption features, as opposed to something like AVIRIS, right? Which is, again, wasn't designed for it, so it has this coarser spectral resolution. But what we found, and found previously to this study, is that for really big super emitters, 5 nanometers is more than sufficient to be able to capture methane absorption. I mean, it works just fine. And really the benefit that you get for something like this is you get really fine spatial resolution. You can think of it as a trade-off space between spectral resolution and spatial resolution. So you can't have both of them. So if you trade a little bit of spectral resolution, you're not going to get small, tiny emitters, but you're going to get really fine spatial resolution. And that allows you to map out individual plumes. And so this image here shows various facilities, oil and gas, to dairies, to a landfill. And you can see the plumes at 2 meter spatial resolution. And so the source attribution is trivial. You just look at it and you say, yeah, that's where the methane's coming from. But again, you're not going to be able to do a total carbon budget accounting for this because it's only sensitive to the big emitters. But we find that the big emitters are significant. So again, here are all these different puzzle pieces. How do we put them together into something that is useful for us, that helps our decision support? And, you know, here I'm just showing kind of in LA, the spatial extent of our observations and the temporal extent. So on the left, you know, I'm showing where do we have coverage from tropomi? Where can we expect to get a retrieval? You see, it's not the whole LA basin, because wherever there's mountains, tropomi doesn't do a really good job and throws out those retrievals. The diamonds represent where our towers are. These blue squares, it's something I haven't gone into, but it's another instrument we have in LA called CLARS FTS. And it basically sits on top of Mount Wilson. And luckily it didn't burn down, but we were all really scared about that for a while. But the fire's not over, so who knows? But it's another spectrometer that sits on top of Mount Wilson and basically mimics a geostationary satellite. So think of it if you had something like tropomi, but that was looking at a slant down into the basin, and it scans the basin. And then we also have AVIRIS, and so I've overlaid where we have you know, AVIRIS flight lines from 2017 to 2018. And on the right is the temporal extent. And again, this is, you know, again, your trade-off, right? With tropomi and CLARS, you can only make observations when it's clear outside, which in LA is most of the time. So usually you can get some observations, but in other regions, you know, that's not a guarantee. And the surface network, you're always getting data. And then AVIRIS is sparse because you have to have money and time to go fly field camping, right? So you get the high spatial resolution, but you can only do it when you're able to do it. So how do we put these together? I keep harping on. And so I'm going to suggest one strategy that seemed to work pretty well for us. And that is to take our towers, our satellite, and CLARS. Now, you know, CLARS wouldn't really be extensible to other regions, but I'll use it for the sake of this study, and put them into a data assimilation framework. And that data assimilation framework gets us from a basin-wide emission estimate down to a kilometer scale emission estimate. And then you use that estimate to then prompt something like an airborne campaign or on-road, but here we have airborne, so I'm using that, to do point source attribution quantification. Okay, so I'm going to start with the top, is this multi-tiered data assimilation. And basically what you have to do is you have to figure out a way, this is inverse modeling, you have to figure out a way to take downwind concentrations and map them back to their upwind emissions. So there's multiple ways to do this, but at the end of the day, you have to simulate atmospheric transport. And so I do that through a Lagrangian approach. So I use a model, STILT model, developed by John Lynn, who's now at the University of Utah. And it's a stochastic time inverted Lagrangian transport model. And basically this mimics, it simulates atmospheric transport. And you do that by, I won't get into the details, but you do that by knowing, if you know where you took an observation in space and time, and then you have an ensemble of theoretical particles, let's call them, and then you let them flow backwards in time with some stochastic component along the winds, but you allow for some stochastic turbulent component, and you let them run for long enough backwards in time, you can basically see where those theoretical particles came from. And if they came from somewhere where you know that there are emissions, then you can say that that observation was sensitive to those upwind emissions, right? And so that's basically, the theoretical framework of it. On the right, I'm just showing, a footprint, which is an influence or sensitivity plot, which basically tells you how sensitive are emissions upwind, how much did they contribute to that purple dot, that observation of that purple dot. And unsurprisingly, the grid cells that are nearest the purple dot obviously contributed the most. If you have a big emission that's close to where you took the observation, that's going to have the most sensitivity. So I run these simulations over 2017 and 2018 for each component of the observing system, from CLARS to Tropomi to the surface network. And here I have just plotted what the average daily sensitivity, or not daily, but just a single overpass, but let's just call it daily, I guess, for simplicity. You can see the strengths and weaknesses of each of these components of the observing system. Basically, if you take, let's just focus on the surface network and Tropomi. If you look at the surface network, you can see you get the maximum sensitivity of any of the other components, right? Right next to where the towers are, you're really sensitive to any emissions right there. But as opposed to Tropomi, if you look at Tropomi, that gets you the spatial coverage. You see there's more sensitivity throughout the basin, right? So it's a trade-off. You have less maximum sensitivity with the satellite because you're observing from space as opposed to the surface network, but you have access to greater coverage with the satellite. So let's just concatenate. Let's concatenate these, put them together in our assimilation system. And so here I'm just showing a very standard Bayesian maximum a posteriori approach that's used kind of extensively in the inverse modeling, methane inverse modeling community, where you basically have some observation, which is y, and then some state vector x, which that's your emissions, and you want to optimize for them, right? And so you do that by creating this cost function that balances the mismatch between your modeled data, which you modeled through STILT, and your observations, and it balances that with a prior emission inventory. And so you optimize this cost function, and you get a posterior best estimate of what your emissions are within the basin. Now, this is a little tricky. This is a little simplified here. Again, don't want to get into the nitty-gritty. You can go read the paper if you want to, but there is some nuance with your error covariance matrices here. And that's how you kind of, that's how you weight any error that you might incur in your atmospheric transport or in your instrument, by adding these. And what tends up happening on these fine scales where you have observations that are near each other, you have a spatial and a temporal error covariance pattern structure and between observing systems. Tropomi, if you take a Tropomi observation, right where you have a surface observation, you're also going to have error correlation. And so these are off-diagonal matrices, R and S, but I'll leave it at that and say there's a little bit of nuance there. So what I'm showing here on this next plot is from 2017 to 2018, I do this assimilation of all these different observations, and here are my posterior fluxes. And I use so Melissa was on the call, I use the EPA gridded massacres inventory to do this. And a few things pop out. One of them is that you get more methane activity up in the, I don't know how well people here know LA, but in the valley area. So that's near Aliso Canyon, Sunshine Canyon landfill. I'll get into that more later. And just the San Fernando Valley generally. You get a little more activity down in the Sunset, Huntington Beach oil and gas fields, and you get a reduction in the San Gabriel Mountains. And for whatever reason, this is a national inventory, but these grid cells in LA allocated a few more emissions than they probably needed to the mountainous region in LA. And so you see the inversion is saying, no, there's not actually that many emissions there. And so you can use something like this. This is a 3-kilometer flux product, and that gets you a long way. It tells you, hey, look, I have a pretty good sense of where my emissions in LA are kind of where my hotspots are, right? Or conversely, where I'm actually doing better than maybe I thought I would, or where the inventories are showing no change. So the inventory's got it spot on. But let's say for the hotspot, that's what we're interested in. Where are we seeing hotspots and how do we interrogate that? So like I said, in the San Fernando Valley area, you have multiple types of sources that could potentially be contributing to these hotspots. One, could just be residential emissions. And so there's a lot of research going on saying that, there's actually more significant residential emissions than we thought there were post-meter. And so that's kind of a distributed source across the, population core. But also in the San Fernando Valley, you have some big emission sources. And that's Aliso Canyon, which for those who aren't familiar, there was a huge oil and gas, blowout several years ago. And it's a gas storage area, and there's also active, oil production there. And then there's also Sunshine Canyon landfill, which is now the largest landfill in Los Angeles. There was a Puente Hills landfill that closed about 5 years ago, but Sunshine Canyon is a pretty massive landfill. And so let's zoom in on that area. So here I have on the left showing from March to April 2017 over the Sunshine Canyon landfill in particular. So now I'm taking my posterior, and instead of considering the full time frame, I'm just considering the very beginning of my inversion. I guess I should mention that when I compute this inversion, I do it on 2-week intervals. So I have a temporal component as well. And I can see that I'm pretty near my Granada Hills at equivariance tower, and that I definitely, in the inverse product, am seeing an enhancement due to this landfill. So something that was very fortunate was that during the same time period, we had Avarice NG flights, and they extensively looked at the Sunshine Canyon landfill, or at least in the very beginning of the campaign, they were like, let's go look at the landfill and see what we see. And what they ended up seeing right at the beginning were these huge plumes coming off of the intermediate face of the landfill. And so that's what I have shown here on the right are these plumes. These are methane plumes at Sunshine Canyon landfill. It was very perplexing. So they called them up. I wasn't at JPL at this time, so I won't take too much credit for this, but I'll take a little bit, but not too much. But they called up the landfill and said, hey, look at this. We're seeing all of this methane. What's going on? And the local enforcement agency spent a bit of time thinking about it. And they were like, we have no idea. Because this wouldn't be a part of the landfill you would necessarily think had a lot of activity. These are, you wouldn't necessarily expect, a bunch of emissions like that would register like point sources coming off of intermediate slopes. So kind of just to back up a little bit, for a landfill 101 is landfill is segregated into 3 major parts. So one's the active or the working face, and that's where the trash is dumped, the regular trash dumping when you drive up to a landfill. So that sits there for a while, and then it gets moved and covered with something called intermediate cover, and that makes up these slopes that are covered where nothing's really happening on them, but they're not permanent. So an intermediate slope will eventually, get plowed and moved somewhere else, but maybe on the scale of a year or 2 years. And eventually, there's a final cover. And so that's where, if you've ever seen golf courses that have been built on top of former landfills, eventually the trash gets buried, they plant vegetation, and they never touch it again. And so they were seeing these big plumes off the intermediate slopes, and we're saying, what's going on? So the local enforcement agency eventually got back to Sunshine Canyon, and they said, yeah, this was a big problem. And essentially what happened was, about 10 years ago at Sunshine Canyon, they instituted a new practice that really backfired on them. And so, again, I'll give you kind of a quick update on how landfill management, what happens is at the end of every day at a landfill, the active face, the working face, has to be covered with some sort of daily cover. And so this can be soil, right? This is like 9 inches of soil that they put on top of all the fresh trash. And that's basically, the reason for that is to keep the odor down and to keep the flies and the birds from, overtaking the landfill. And then what happens is when they come back to the landfill the next morning, they scrape off that daily cover and they keep dumping trash on it. So it's an iterative process. They have to do this every day. Well, about 10 years ago at Sunshine Canyon, whoever was operating right then, and I think it was actually the municipality that wasn't the operator, or at least they claim wasn't the operators of the municipality, said, you're wasting time, stop peeling back the daily cover. Just leave it on there and pile more trash on top. So basically what was happening is they were creating, for lack of a better word, a trash lasagna, where it was this stratified layer of trash, then soil and trash. Now, you wouldn't think that this would necessarily be a big problem, but just remember, trash is extremely disgusting. And what happens is as it sits there and decays, there's leachate, right? There's a lot of water in trash. And so this leachate, this like garbage juice, goes and pools down to the bottom of the cell, of the intermediate slope. And they'll usually divert it off into a leachate pond. Well, because they were not pulling back the soil from the face of the landfill, it meant that the leachate was being perched closer to the slope. And it was producing a lot of methane and was just blowing out the side of the intermediate slope. So, it was a very poor management practice that I think they had good intentions. They thought that, if we don't take the daily cover off, then hey, we're actually going to cap more stuff off, when really it worked in the opposite. So credit to Sunshine Canyon. Over the next several years, they instituted some pretty dramatic infrastructure improvements. And that basically came down to there's 3 main things, but 2 that really had the biggest impact. And one of them was installing closure turf on top of the landfill. So think of that as just like astroturf, artificial grass that they just put on top of the landfill and then poked holes inside of the closure turf where they installed wells to collect the gas. And then they also put posi shell. And so this is a cement fiber mix that they basically put in a sandblast tube and blasted all the landfill with to try to cap these emissions. And the funny thing is, it worked. And we imaged it with Avarice, this whole campaign. The campaign started in 2016, and all the way through 2018, the Avarice NG was flying over while they were doing these campaigns. So look, so on the left here is now October 2017, after they put in the closure turf and the posi shell, and those plumes that we saw have just mostly disappeared from the face of the landfill. And if you look on the right, the blue line are the odor complaints from the surrounding community, and the red dots are the integrated methane, the mass of methane that we quantified from Avarice NG. And you can see the correlation is very good between the two, that we really see this sharp reduction in methane and in odor during the time that they are implementing these infrastructure improvements. And what's even more exciting is then if we go back to our inverse product, we can see that we see this reduction in the inversion, right? So if you look on the top right panel, that's that original, March to April 2017 inverse flux at 3 km, and by March to April 2018, we see a substantial reduction in the emissions. And if we plot it on a time series here on the left, with the gray bar being that time varying inverse flux product, there's a significant decreasing trend that correlates relatively well with the Avarice NG derived flux rates. And so it's a nice story of really this end-to-end analytics framework, right? Where we can go from the coarse, from the inverse product, get to something that's more regional, and then get to the fine scale, show that there's some sort of decision support, and then be able to validate it. And we hope, this is kind of a prototype framework, but this is something that we can do in other regions. And even if we don't have, the luxury of so many observations that we have in Los Angeles, we definitely have Trobomi, and soon, which I'm going to get to next, our ability to do fine scale point source mapping from satellites is rapidly increasing So we can start replicating these types of studies in other places as well. Okay, so that ends my part 1. I can take questions now, or we can wait to the end. It makes no difference to me. Any preferences? Maybe I'll keep moving.
Yeah, let's keep going.
Let's keep moving. Okay, so part 2, what can we do from space, right? So I've already shown a little bit what we can do with tropomi, which has just been incredible. But we can actually, we're going to start to be able, well, we can already, and even more so in the future, be able to do a lot more. And so I want to draw attention to 2 satellite imaging spectrometers of several that have launched or will launch in the future. And so this is actually work, Cynthia's on the line that worked on with Cynthia. But here I'm showing on the left a transmission spectrum from different instruments. And I alluded to previously kind of the trade-off space between spectral resolution and spatial resolution. And so you see this tropomi, this 0.25 nanometer spectral resolution. I have plotted here just a transmission spectrum of just a normal atmosphere. And so, right, tropomi is really trying to get these fine absorption features, which is great because you have better precision on your column methane, whereas something like average NG is much coarser. That's the red line. Well, we have a few satellite imaging spectrometers. Again, these were not designed for greenhouse gas monitoring that are set to launch soon. And actually, Prisma has already launched. And I'll show some results from Prisma. And these have even coarser spectral resolution. So this is like 10 nanometer spectral resolution. But again, for really big sources, that might be sufficient, right? And I'll show that it's sufficient. And, so these are just 2, but I'll also just, list them here. So Prisma, this is Italian Space Agency, NMAP, German, EMIT, which is JPL, NASA JPL will fly on the International Space Station. That's probably 2022. SBG, Surface Biology, Geology, Decadal Survey, Designated Observable. That's, 2025. CHIME, Chinese instrument, same time period. There's also a suite of other satellites. So I want to say, I'm focusing on imaging spectrometers here, but I'm sure many of you already know of GHGSat, which, there's been so many exciting results from GHGSat, and they just launched their 2nd instrument, which is a different type of instrument configuration, but with that, we're looking at, the same type of 50 meter or so spatial resolution. And of course, there's Methane Sat, which is in the works as well. And the EDF colleagues that I saw on the phone, I'm sure, are very keenly aware of that. And that's, we're getting at kind of this in-between space where we're at about a kilometer resolution. So in between what the fine scale point source mapping of a imaging spectrometer, but much, much finer than something like tropomi. So you kind of get the benefit of both. But I'm going to just focus really on Prisma and mostly Prisma, but NMAP will have a similar instrument configuration. So I said, I think for big enough sources, we should be able to still get some methane. And one of the reasons I say that is because of some theoretical work that we undertook a while ago to generate a lot of synthetic scenes. And so basically taking these WRF LES, and so this is a model, WRF LES is like a fine scale plume model, and we simulated a bunch of methane plumes with WRF LES, and then generated synthetic atmospheric spectra using from NMAP. They have a synthetic NMAP spectra tool that they have that we then just included, horizontally varying methane to it to generate top of the atmosphere radiances that we would expect to see from NMAP over a variety of surfaces. And so we did it over grassy surfaces, heterogeneous surfaces, bright surfaces, dark surfaces. And so on the top panel are the results from the synthetic study, and where we saw this is a 900 kilogram per hour plume. And on the left and on the right is the retrieval. So you see there's noise, certainly, but it's definitely picking up, the plume, and it can see that. And so 900 kilograms an hour, that's a big emission, but it's not an unexpected or unheard of emission rate, especially for a super emitter, if you, peruse the literature of the magnitude of super emissions. And then on the bottom, we did, this is also synthetic, but it's a little more based in data where we took average NG spectra from known methane emission sources, and then we just downsampled and rescaled to what an NMAP equivalent spectrum would be by computing the additional transmission through the atmosphere and doing, adding the respective noise that we would need to get to the sufficient SNR. And we see that we're actually able to also be sensitive to those emissions. And it seems like we have a little bit of a bias. Maybe we're biasing a little bit low, if anything, but we're certainly, that's more in the emission quantification, but really we're seeing the same emission patterns, right, for these big sources. And so this is a theoretical study that we did. We said, that, you know, made us really optimistic. That was like, hey, this is something we think we can do. But Prisma launched in 2019. And it just so happened that in November of 2019, so about 7 months after Prisma launched, there was a gas blowout in the Eagle Ford Shale in Texas. So this is Devon Energy, who I say because we actually have a pretty good relationship with them. So they were on board with this study. But there's a gas blowout there, and we were able to target the instrument to look at that blowout 15 days after the blowout had started and after flaring had been applied to the blowout. So the event started on like November 1st. It took about 14 days for them to divert the gas well enough so they could apply flare to it, and it flared until the 20th. Okay, and so we imaged it on the 15th. And we also tasked SkySat, which, if you're not familiar, this is Planet Labs 70 centimeter visible imager. And so that gives you a really good high resolution look at what's happening on the ground. But what's interesting is we said, okay, here we have these spectra of a known event. Let's try to retrieve methane. And we did, and we saw a significant plume right downwind. And we said, well, hey, guess what? An imaging spectrometer is not only sensitive to the methane absorption bands, also sensitive to the CO2 absorption bands around, you know, the 2100 nanometer band. Let's do a CO2 retrieval. So we did that as well, and we also saw a plume. And so when we said, okay, well, we have methane, we have CO2, we know something about the composition of that well through Devon and through other independent surveys that have been taken at the Eagle Ford, why don't we compare the emission rates and try to get a combustion efficiency estimate? And so we did that, and we estimated about 87% combustion efficiency. So first time really from a satellite that we've been able to quantify a plume at this scale and also quantify combustion efficiency. So it's actually a really exciting possibility of future studies that we can do. But getting back to the tiered observing sense, it was not just Prisma that was looking at this, right? We had Tropomi looking at this, and our colleagues at GHGSat also were able to target this plume. And so, you know, from some of the great work that's been done by Elvidge, from Chris Elvidge, about trying to infer emission rates from VIIRS flaring, nighttime flaring data sets, we were also able to estimate an emission rate from the VIIRS flares. And we were able to create this time series of emissions over the course of the event. And so now it's not just a snapshot of an emission, but it's really being able to capture the dynamics of these events that we can get at entirely from space. So if we take this time series of emissions and integrate it, we get about 4,800 kilograms lost of methane. Actually, I think that's an error. Sorry, I forget what the actual number is. But anyway, the only thing to remember here is, I think my units are wrong. But when we did our bottom-up sense, we used the Oil and Climate Index, which I think has some Stanford buy-in as well. I'm not quite sure of the affiliation, but it was Deborah Gordon, our colleague at Brown University, the Watson Institute at Brown University, also ran, we looked through the leases of this particular well pad to see what was the actual reservoir pressure and what could potentially be emitted in methane over this same time period. And we ran that independently through this Oil and Climate Index. And again, regardless of the units, it was a very close correspondence between the two, which helped us think maybe we can start getting at the total dynamics of these types of events. And so that's an exciting opportunity. And I guess I'll just kind of end with saying, you know, Prisma has kept observing stuff. And so this is just some unpublished work, but just to whet some people's appetites of we can get plumes all over. And here I'm showing a landfill in Lagos, Nigeria of 11,000 kilograms an hour. So that's more than 3 times bigger than any landfill that we imaged during the California methane survey. It's just a massive plume coming off of kind of an unmanaged landfill in the middle of the city. But also up in Turkmenistan, these are Prisma acquisitions and retrievals of 2 oil and gas facilities kind of in the boonies in Turkmenistan. And what's important to see is like the one in the middle, our emission estimate's about 35,000 kilograms an hour. And just to put it in context, Aliso Canyon, the big blowout in LA that generated so many headlines, and that was about 50,000 kilograms an hour and then reduced to about 20,000 kilograms an hour over its several month period. So we're talking about something that's, you know, kind of happening in the middle of nowhere, Turkmenistan, that's totally not quantified anywhere, any emissions, but that we can start getting at with satellites. But, you know, what it's going to take is not just these one-offs, right? Because, you know, that we don't get persistence in the emissions with just one imaging spectrometer like Prisma. As great as it is, right? It can only target a certain number of sites per day in its 6-day revisit, and it needs clear sky operations. And so there's no way we're going to be able to quantify a total global methane budget with just this one instrument. And that's why I keep coming back to, you know, using things like EMIT, using things like NMAP, using things like methane sat. It's really in all of the GHG sat. It's an all of the above strategy, and it's a synthesis strategy. But we've seen enough examples now from instruments that are already in space that were out of the realm of theoretical, like can this work? This can work. It's just now coordinating the data sets and really, you know, coordinating the way that we put them together and think about it. Okay, well, that is all I got. So thank you.